the year model design, we have some basic rules or principles we need to keep in mind. The first one will be faithful in our design for the year models. So whenever we model real-world applications, we need to ask ourselves what are the information we have, as well as the constraints on both the entities as well as the relations. In this page, we show three very basic examples of the year model design. So the first one models a person may purchase some product. And we've mainly focused on the cardinality constraint on the purchase relationship between the person and the product. In the real world, we know that a person can buy multiple products at the same time. According to this year diagram we show for the first case, we find that we have one arrow pointing to the product. In other words, we follow the direction of this relationship as well as the arrow. We say that given a person, we can always find one single product purchased by the person. Is it correct or not? Since we know that in the real world, a person can buy multiple products simultaneously, we cannot add an arrow here. And the second example denotes a person can be the president of a country, and we model the relationship between the person and the country. In the real world, we know that at a moment, a person can be only the president of one single country, right? And given a country, we can only find one single person who is the president. In other words, the cardinality constraint on this president relationship should be 1-to-1, right? However, what we draw here is many-to-many. It's not correct. Therefore, we may need to add the arrow pointing to both the country as well as the person, right? It will be 1-to-1. In the third example, we want to model an instructor can teach courses. We know in the real world, an instructor can teach multiple courses. However, for a given course, we only find one single instructor who teaches this course, right? In the example, we show this teacher's relationship between instructor and the course. It is many-to-many. However, we know that given a course, we can only find one single instructor, and we have to add one arrow pointing to the instructors, right? It is 1-to-many instead of many-to-many. In other words, this design is not correct, and we have to correct this into 1-to-many state. We just show these three examples, letting you know we want to be faithful in our design for the year models. Another important principle we need to keep in mind in designing the year models is to avoid redundancy. This is also very important because redundancy can occur whenever we say the same thing twice in different ways. This redundancy can be created very easily, however, we can ignore them also easily. And redundancy can be very bad, of course. It can waste lots of space in storing this kinds of redundant information. Another more important disadvantage of redundancy is that it encourages inconsistency. Because for the same thing we say multiple times, and sometimes we can make some changes or updates to this kinds of information. And we also need to do some updates of this information sometimes in our tables. And we may forget to update all these kinds of redundant information at the same time. Then it may create not so inconsistent information in our tables. This will be very bad. In the bottom, we have an example. Like we have two entities. The first one is the beer. The second one is the manufacturer. For the beer, we have two attributes. The first one is the beer name. The second one is the manufacturer information, or the name, for example. And on the manufacturer, we have two attributes. The first one is the manufacturer name, as well as address of the manufacturer. Between these two entities, we have one relationship. It is manufactured by. It denotes a beer is manufactured by some manufacturers. And this relationship follows is a many-to-one constraint. In other words, whenever we have a beer, we can always find one manufacturer which produces this beer, right? We have one arrow pointing to the manufacturers. However, for this design, we have some problems, right? Because for the beer, we already have the manufacturers, this information here. And in the manufacturer side, we have the name again. And the manufacturer information for the beers, as well as the information here, may create some inconsistency. For example, we have a beers table as a separate table, and manufacturer as another table. Probably we can update the manufacturer name sometimes in the manufacturer table, and we forget to update the manufacturer information in the beers tables. Then they will be inconsistent with each other. So this design will be very bad. To solve this problem, we can have another design like this. We can just create one single entity, beers. For the beer, we have information. The beer's name, we have the manufacturer name, as well as the manufacturer address. Is this design a good design or not? This will create lots of redundancy. How can this be possible? Because in this design, we have to store the same manufacturer name as well as address multiple times if the manufacturer produces multiple beers. If we store the same information multiple times, then it will create lots of inconsistency. A much better design will be like this. We have a beer. This beer has only one single name. And we have one manufacturer, this entity. It has a name and an address as attributes. Between them, we have this manufacturer by this relationship. It will be a much better design. And this design will give the address of each manufacturer only once. It will create no redundancy. I can also use one example to compare these three different designs with some concrete data we have. Okay, so to compare these three different ER model designs about the same information in the real-world domains, we want to show the difference by using some concrete data we can connect from the real world. Let's assume we want to model some data here. Now the Bud and the Bud Light, they are manufactured by Bush. This is the manufacturer, the name, with address 2700 South 9th Street in St. Louis in the US. And how can we model these kinds of information we have in the real world? According to our previous descriptions, whenever we have these ER models, we have to translate them into relations so as to generate some tables, right? Here, let's assume we can generate the tables for these three different ER model designs we showed before in the slides. So for the first one, for the beers, we have both the name as well as the manufacturer name information here. For the second one, we just have one entity. It covers the name of the beer, manufacturer name, as well as manufacturer address. For the third one, we have two entities. For the beers, we will have the beer names, and manufacturing information will be all here in this entity. And we can show the difference by drawing the tables, so you can know why this third one is better compared with the previous two. Okay, let's do the first one. So we have the beers as an entity, so we may have to generate a table for beer, right? And we can write down the table name here, beer, and we can move beer here. This table has two columns. The first column denotes the beer name, and we can use a small font. And the second column denotes manufacturer name. This is for the beers table, right? According to the data we have two different beers. The first one is Bud. We can just write down Bud. The second one is Bud Light. We know they are manufactured by the same producer. It is Bush, right? B-U-S-C-H. So this is the table we can create for the beers to model, to contain the data we have here. Besides the beer, we also need to generate a table for manufacturers, right? So we can copy it and then write down the name. It will be manufacturer. So in the manufacturer, we have the manufacturer name, right? And the manufacturer address. Since we only have one manufacturer, so we can delete the second column and also shrink the dimension like this. The manufacturer name with Bush, the address will be very known. Right? We can use a known table and also adjust the dimensions for the first column. We can copy the address information here. We can use small font like this. So this is a manufacturer table. Besides this, we also have another table for the manufacturer by. It's a relationship. We also need to translate this relationship into a relation. I will show the details in the next section, how to do the translation. Here we can do, let's assume we have a table created already, and it's called manufacturer by this table. Right? This table has two columns. It contains a key from beers as well as a key from the manufacturers. Here we assume the name of the beer and the name of the manufacturer can serve the keys. Therefore, the table for the manufacturer buyer will be like this. It will be a table with two columns. We have beer name as well as manufacturer name. In other words, this table will contain exactly the same information as the beers. Then you can see why we say this kind of design is redundant, because we save the manufacturing information multiple times, here as well as here. And these two tables are also redundant, right? Besides the redundancy, it will also create not so inconsistent. Let's assume if in the near future we want to change the name for the bush. Now we can change the name bush to ambush. After we do the changes here, we also need to do the changes in this relationship table. This can be done very easily, and in the near future we will show why we can do this easily, because we have some automatic changes, rules, or policies for the relationships. However, for the entry in this peers table, we also need to update all these manufacturer names. This cannot be done by the system. We have to adjust this name manually by ourselves in our program if we do changes here. So therefore, if we do changes, we also need to update all these entries, right? As well as all these entries. If we forget to update these entries, then we can have inconsistent manufacturer name in these two tables, in the BS table as well as the manufacturer table. Right? Therefore, this design is not very good. Now we have to redesign this into a pseudo one state. And let me recover all the data we have. Okay, we have shown that the first design is not very good. It creates also redundancy and also introduces inconsistency in our data storage. And let's come to the second case. If we design an ER diagram like this, what can be the problem? Since here we only have one entity, the table will be also very simple. Right? We only have the beers table. We can copy this table into this card. However, for the beers table, it will be much more complicated. Right? It has three attributes: the beers name, the manufacturer name, as well as manufacturer address. Therefore, we have three columns, and the third column will be the manufacturer address. And the manufacturer address is very complicated. Let me copy the strings here. According to the representation of the table, we find this table can be good because compared with the first case, this table is much smaller. Right? However, it is not the case. Let's see the third column for the address. We find this address is very complicated. It has a very long string. It contains exactly the same information. However, we store this data multiple times. Maybe it is not very obvious. Let's add more beers, for example. Beside the bud and the bud night, let's assume this bush has other bud. Now, bud 1, bud 2, bud 3, and bud 4, for example. We want to show some extreme case, right? This design can have some problems. They are all produced by the bush, right? The address will be stored multiple times, as you can see. So you can see this ER model design may also introduce not so a redundancy, because we store the same information, the same data multiple times. It will be much more obvious as we have more data stored in our tables. We store the same data multiple times. Besides redundancy, it will also introduce inconsistency. Let's assume in the near future we want to make some changes to the bush address. And we find that the bud is produced by a bush, and we want to change the address up to 2000 instead. However, since we have so many beers which are produced by a bush, and if we forget to change the remaining ones, then we can have inconsistent address for the manufacturer. In other words, in this design, due to the redundancy, we may also introduce not so inconsistent if we have some updates on the data we have in the tables. Right? Therefore, this design is also not good, and we have to avoid designing the ER models in this way. Let me delete these rows and recover to the normal case. Okay, so the second design is not good either. Let's come to the third design. The third design is very similar to the first one. The main difference will be for the beers table. We don't have the manufacturing information anymore. And the table we can have for the third design will be very similar to the first one, except the first BS table, we need to make some changes. For this BS table, we have to delete this column. Then it will be the table we can have for third design. By checking the third design, we find that it doesn't contain any redundancy, and it is also very easy to maintain the data we have in the tables, and we can avoid this inconsistency very easily. Right? You can find we have some duplicate information here as well here. The beer name was stored multiple times, as well as bush name, as well as the manufacturer name was stored multiple times. However, this kind of information can be handled by the system with some rules easily. Someone may claim if we make some changes to the manufacturer name, actually the system can do the changes in the manufacturer by this relationship table automatically by the system. Similar for the beer's name, if we change the button name, the system can also change this button name here in this table as well automatically, because it is a relationship between this beer and the manufacturers. We will show this later as we talk about the SQL. So this design will be very good. It doesn't introduce this redundancy, and it can also control this inconsistency very well.